I'll just give that a moment to kick in. Perfect, lovely. Okay, well, welcome everybody to our first open source satellite meetup of the year, which is quite exciting. I'm not quite sure where the year is going, but anyways, here we are. For those of you who haven't been to one of these sessions before and perhaps haven't met me, so I'm Vicky Anderson. I'm a senior system engineer at KISPE. Luckily, I haven't got to hear too much from me today. I'm going to be handing over to two of my colleagues who are going to tell you some exciting news about some hardware that we're releasing out into the wild. So I'm just here to top and tail and help coordinate the session. What I would like to say is if you have any questions throughout the session, please feel free to pop them in the chat. I will make sure we collate them and go through them at the end, but we do have a Q&A session at the end where you can quiz my colleagues or perhaps anyone else from my team on the call about what it is that we've been up to, and we'd love to get your thoughts. I think, Paul, if you just hop on to the next one. I'll just do a bit of a blurb because it is the start of a new year, and some of you guys might be new to this, to what we're doing, and kind of wondering what it is, we're actually all about and what this open source satellite program is. So I wanted to give you a very quick kind of overview of what it is we're trying to do. Now, hopefully everyone on this call can appreciate, space really does have the ability to change lives, the ability to use space under a whole number of different kind of avenues, whether that be for commercial purposes or for things like most recently looking at kind of disaster monitoring and kind of being able to see the scale of impacts in certain areas, and, for the facilitation of getting aid to places that are required. Space is a really useful asset, and I say it has that ability to change lives and, to do a lot of good. And there are people out there with loads of fantastic ideas, but they literally can't get them off the ground because of this cost barrier of the entrance to, getting into space. As you probably appreciate, space is, it's a tricky and pricey endeavour. And at KISPE, we're really keen to kind of grow and develop kind of the space market and the space ecosystem, but we really want to do this in a sustainable and responsible way. And so, we thought about what we could do here, and what we've developed and what we're moving forward with is something we're calling the open source satellite. Now, you might think, well, what's so special about this satellite? And the idea is we want to make a platform. So it's 25 to 250 kilograms, and it's going to be collaboratively designed, as kind of Paul and Kevin will talk to shortly. And we want to pull together this platform which has microsatellite performance, but at a CubeSat price point. And for those of you who aren't familiar kind of with some of those terms, I'll give you a quick kind of quick summary now. So CubeSat, you may be familiar with. It's kind of like, say, a shoebox size satellite. They came out of academia kind of in the early 2000s, and they've really exploded as a way for people to get things up into space kind of, I'm going to say, quickly and cheaply, in inverted commas, as cheap as space ever is, and to use them to kind of, for applications for commercial purposes. But the problem with a CubeSat is its form factor. Physics is a limiter. We haven't yet found ways to break physics. And so with that CubeSat kind of form factor, you're limited with regards to space. If you want to put an imaging payload on, for example, you're limited by the defined space remaining in a CubeSat. Also, because of their constrained size, it can be tricky to put a lot of kind of bits inside them. So, quite often CubeSats only have a single string functionality, which means, you only have one of everything. So if something breaks, your CubeSat may no longer work. And also, they can't always be as performant or reactive as a bigger platform because you're limited by the size of the things you can put in to control how your satellite works. So what we would like to do is generate an open source microsatellite platform. So microsatellites are bigger. They're the kind of the next size up from CubeSats. Say we're talking about 25 to 250 kilos, but make it the price point of a CubeSat, as illustrated by the little figure on the right hand side of the slide there. So that's how we're looking at being disruptive and changing the market. And the idea is to make this design available to the open source community to use. You know, for their own missions and to go on and develop and do other things with. So really what we want to do is take some of that initial upfront cost out so people can get their really cool and neat ideas up into space. And with that in mind, I say very excitingly today, we have our first hardware release, which is going open source, which we're really excited about and really keen to share with you guys today. So I'm going to hand over, I think, first to my colleague Kevin, who's going to do some instructions, and then to Paul. And I say, any questions through their talk, feel free to pop them in the chat, and I say we'll do a bit of a Q&A at the end. So Kevin, I'll hand over to you.
Hi, yeah, thanks, Vicky. Right, so my name's Kevin Manser. So I work at KISPE as an electronics engineer, and I have been responsible for the design and development of the board that we're going to talk to you about today. So I will actually be handing straight over to Paul in a minute as the next introduction. So I'll be talking to you a little bit more in a few minutes' time. So over to you, Paul.
Thanks very much, Kevin. So yeah, I'm Paul Madle. I'm a senior software engineer, also working for KISPE. Very excited about the open source satellite. Excited to be here today to be actually introducing our first bit of hardware that is now open source and on GitHub and available for people to download and modify and use. So what we're going to talk about today, we're going to give a little introduction, which is basically the story so far. How have we got to where we are with the design of this particular board? Then Kevin is going to talk to us about and give us an overview of the board with all of its features and that kind of thing. Then we're going to talk about how it can be used and how to access the design through GitHub, etc. So Vicky did a great intro to what OSSAT is, but one of the things that we really want to achieve with OSSAT is a highly integrated design. Whereas, you know, quite a lot of satellites are designed with a sort of distributed architecture with some kind of, you know, onboard bus hanging things together. We wanted to go for a more highly integrated design to save mass, to make it cheaper to produce, and to save power. And with those attributes, those are then attributes that we could give to a possible payload that might sit within the confines of the satellite. So in order to achieve that, we needed a reasonably capable computer at the core of the satellite. Now, with this computer, there are a number of important factors that we took into account. Performance per milliwatt of power is really key. And we wanted something that was performant, but not too performant. And the reason for that is that, you know, we've got experience of developing onboard computers that are very capable. Actually, they're specs, you know, they're over-engineered. They got more capability than you need. And the problem with that scenario is that there's a temptation to make this computer not only perform some of the platform functions, but also to, you know, stray into what to control, for example, the payload. And what we really wanted to achieve with the OSSAT design, because it is open sourcing the design of a spacecraft platform, we wanted a clear delineation between the platform and the payload. So we want a computer that's capable, performant, but not too performant, if that makes sense. So low electrical power consumption is an obvious need on a spacecraft. We've only got solar power with a limited amount of you know, power generation. Simple to manufacture is quite key, and capable functionally of doing various things. So handling CCSDS communications to and from the ground. We wanted something that could, you know, a computer that can handle everything from the data link layer up. Interfacing to many different bus architectures, including analog interfacing, running AOCS algorithms. So the algorithms that that control where the spacecraft's pointing. We wanted to be able to run those algorithms up to 12 hertz. Memory interfacing was key because we need to store and forward lots of platform log data. So that could be error log data, or it could be telemetry data, data that's captured on board that is relayed to the ground later on. And we needed to be able to run spacecraft schedules. So you know, what we call operational timetables, but essentially it's a list of instructions. You know, at 2 o'clock, Mr. Satellite, please do this. At 3 o'clock, please do that, etc. So those are the kind of functions we needed the computer to do. And we performed a selection process with one of our collaborators, Mauricio Di Carvalho, a few years ago now. And we came up with some quantitative criteria: a minimum of 200 million instructions per second, must consume less than 300 milliwatts, floating point operations were needed, able to access 64 megabytes of memory, and be able to withstand that thermal profile, -40 to +100. And there were some other things that we looked at as well. Other criteria which are less quantitative. So things like, you know, how good are the tools that we can use to develop the software that runs on this processor, and are they open source? External memory interfacing, you know, the capability there. Radiation tolerance. So, you know, we've got a rich history of using commercial off-the-shelf components in space. So, you know, one of the key aspects is, you know, how good is this particular processor against the radiation environment, which you see in space. And there's a link right here to another YouTube video, another meetup that we did a little while ago, and you could have a look at that, and that gives you an overview of the space environment and that kind of thing, and the kind of problems that you see there. Then you know, an ability to run a real-time operating system, one that is open source. And then some other aspects, so things that would benefit, you know, the communications type functionality that we needed. So the ability for the hardware to generate and decode and encode CRCs, cyclic redundancy check, to encode or encrypt and decrypt algorithms, to, you know, if there was hardware acceleration to help us with that, because that's quite often a requirement on the space comms. Authentication, flight heritage. So how many times do we know that this processor has flown in space? And then finally, obsolescence. What's the chances of this thing going out of production quite quickly? So we evaluated a whole load of processes with regard to this all that set of criteria. We looked fairly widely at quite a range of different options. One that was, you know, is quite traditional, you know, used a lot in the space industry. Something that was developed by ESA is what's called the Leon core. So that's a IP core that you can instantiate in silicon in an FPGA, or you can buy, you know, these Leon processors already instantiated, and there are multi-core versions of those now as well. But it is a Spark architecture. It's quite an old processing architecture. So from our point of view, it drew too much power and it was too slow. But it's been designed with radiation in mind. Then we looked to another option in terms of FPGAs and that sort of thing, which is micro-semi. We looked at a few different options there, but again, there was a little bit too much on the power side, and the design, as a result of, you know, the choice of FPGAs can push the complexity of the design up a little bit. But it's highly configurable because you have a FPGA. You make your hardware do whatever you want, and there are radiation tolerant options if you need them. Then we also looked at RISC-V, which is kind of cool and trendy certainly within the academic space. But at the moment, at least, there are immature. The products are immature. There's low flight heritage. There's not many people flying these things in space as yet. But it is open source hardware, which sounds good. Basically, that means that, you know, when you buy a processor, a RISC-V processor, you don't necessarily have to pay a charge to the licensee of the processor technology. So, for example, ARM, who get a little kickback every time you buy an ARM processor. They get a little bit of money. So that sounds good, but to be honest, with the volumes of things that we're producing, we're never going to see that benefit. But on the other hand, the RISC-V are good on power because it is a RISC architecture that competes with ARM sort of technologies. Texas Instruments, we looked at that. We looked at the TMS 320F283, which seemed to fit the sort of bill. An interesting processor. It has high reliability it meets high reliability requirements because it has a lock-stepped architecture with two processors running in parallel. There are radiation tolerant options, but again, power was a bit of an issue. The design was going to be quite complicated in terms of the lockstep processor type idea. And the tools that you use to develop the code for these processors are quite costly. There's less in terms of the open source compiler tool chains and that kind of thing. Then we looked at NXP, looked at the NXP 1MX RT1064, and that seemed pretty good. Quite a decent amount of processor power, over 1,000 million instructions per second. It's low power, got a floating point unit. But where it was beginning to not be so favorable in terms of its competition with other processors is that had a limited amount of ECC protection. So ECC is error correction code, and it's something that can be used to combat the effects of radiation on the silicon. So bit flips can be corrected on the fly by this error correction code technology. Renesas, we looked at the RX72, too much power, but otherwise looked okay. Then we had a look at Microchip, and Microchip bought Atmel a little while ago, or they've got the license to use their technology. So we looked at two Atmel devices, one called the SAM V71. It's very common in automotive applications, and the SAM A5D3. And the SAM V71 is an interesting one because it is an ARM M7 core that they actually produce a radiation tolerant variant of that ARM M7 core. And to my knowledge at the moment, I think they're still the only company that are producing an ARM M7 processor that is rad tolerant. But it has, again, limited ECC because we wouldn't necessarily be flying the rad tolerant variant. We'd be flying the commercial variant. But there is it doesn't demand a lot of power, and there's enough processor speed and a floating point unit. And then finally, we looked at STM32. That came out, cutting a long story short, that came out as our winner. It has extensive ECC on all of its embedded memory. It is low power. It's got enough processor speed, has a double precision floating point unit, and people already fly STM32's processors in space. It's nothing new. The only downside is that the thermal side, so it didn't quite hit 100 degrees C, but a little bit more systems engineering is required to cope with that. So we took the three best that we found, and in that selection process, and we, despite the fact that some of these have flown in space, or variants of them have, we wanted to know for ourselves, okay, how will they be able to withstand the space environment? So we took the SAM V71, the SAM A5D3, and the STM32H753, and put them into a radiation chamber at the University of Surrey. On a project in collaboration with the University of Surrey through some money that we managed to get through the Sprint program, and we irradiate them in this radiation chamber. And the good news is that all three of them passed in terms of total ionizing dose radiation. All were okay up to 70 kilorads of total ionizing dose. The failures observed on the failures that we did observe seem to be on the on-chip flash memory. So this appears to be the weakest part. We certainly saw the ECC on the flash memory being exercised on the SAM V71. And we saw that the STM32 seemed to be behaving in a similar sort of way as the radiation dose went up. And it's likely to be that it was the flash memory that was causing the issue. We didn't actually manage to kill the SAM A5D3. That was pretty good from a total ionizing dose point of view, but it doesn't have any internal flash memory. So it's not quite a like for like, if that makes sense. But the details of the results are on our website at those three links on the opensourcesatellite.org. And we want to perform further testing because total ionizing dose is one aspect, but we also want to see how the processors handle some of the other effects of radiation. So the single event upset, where you have bit flips in the memory, basically. And a way of doing that is to fire protons or heavy ions at the target processor, and we want to do that this year. To figure out how well the ECC in these chips fix the bit flip problems, and how much abuse can we give them before they start falling over, and are they suitable for the missions that we want to put them on? So the STM32H753 has some key features. As I said, it has ECC protection on all of its internal memory. So the program memory, 2 megabytes of that. Data memory, it's got an internal SRAM, which on-chip SRAM, which is 1 megabyte, and the cache memory also has ECC. So if we manage to do some radiation testing with heavy ions, protons, maybe we could have a look to see if we could leave the cache memory on and see how well the processor copes with the cache memory actually on, with the ECC correcting failures on the fly. Yeah, I mean, usually cache memory is the thing that is the most susceptible aspect of the processor because of the feature size of the transistors within it. So it's got some good open source development tools with a development environment called STM Cube, which uses a GNU cross compiler toolchain. And it has a simple debugging or a inexpensive debugging option using a technology called ST-Link, which ST sell themselves. And there's plenty of support for RTOS, and actually you can get free RTOS running within minutes, on this process. So there's a lot of support software-wise. It looked really good, and it was certainly fast enough, but not too fast. 1027 DMIPS. And in our test, during our radiation test, we had it running that fast, and it was consuming around 230 milliwatts. So it's good for AOCS algorithms with a double precision floating point unit, and it's good for space comms because it has an embedded hardware accelerated CRC encoding and decoding, and DES, triple DES, and AES AES encryption and decryption hardware accelerated as well. And it has a flexible memory controller and lots of I/O options. And I will leave it to Kevin to describe those I/O options and what we've actually integrated into our design. So now talking about this particular board, before I hand over to Kevin, as a way of intro to it, we've basically created this development board that allows you to run and develop the OSSAT onboard software. It's based on the same architecture as our flight onboard computer, but with a few differences. There's a different form factor. It includes some debug hardware not on the flight model. It has a different grade of parts. So all the parts are commercial off the shelf, and we are going to fly commercial off the shelf components. But the parts on this development board haven't passed our flight part selection process. It uses different memory. On the FM, we're using MRAM, external memory, but we recognize that it's a bit expensive. So on this board, we used SRAM, and it was SRAM that we could get hold of as well, which was a bonus. And it has a lower amount of memory than the FM model. So the FM will have 40 megabytes of external memory. This board has 8 megabytes. And code runs, and the code that runs, but the key is really that the code that runs on our FM board also runs on this development board with no alterations. So now I'm going to hand over to Kevin to talk through the actual board and the features of it.
Yeah, thanks very much, Paul. Right, so let me introduce the board. There's a picture of it there. So what I'm going to talk about is its functions and features. I'm not going to go through like the schematic diagram at all, because I don't think that would be particularly appropriate to everyone in the audience. So that's really the philosophy for this this talk. So what we're doing here then, we're providing a convenient hardware platform for collaborators to develop satellite firmware. As Paul's already mentioned at length, it's based upon the STM microcontroller. It includes various interfaces for connection to other satellite subsystems, and obviously you will be free to use those however you wish. It's got a programmer debugger interface, which Paul has alluded to, and I will describe in a little bit more detail further on. It does share several attributes with the sister board that is being developed as a flight model for a space application, and that might well become apparent. But unlike the flight model, it is actually powered from a USB power supply, which is nice and convenient for people to use. Go on, Paul. Thanks. So this is a picture of the board. I won't dwell on this one too long. I will just quickly explain that towards the right-hand end is the actual main computer functions, and then more towards the left we've got the extended area, which is intended for providing ease of debug and connectivity. And also you can see on the very left-hand side there's the little USB connection for power. Okay, so a few features of the board. It's a 6-layer PCB. Done mainly, we probably could have got it on 4, but 6 layers provides a nice topology for ground planing to ensure good signal integrity and functionality. The particular STM processor is mentioned there. Paul's already mentioned the fact that it uses SRAM, so it is actually 2 static CMOS RAM chips on the board. ST-Link programming and debug interface, that actually includes a UART, which is quite convenient because you can obviously use that for additional status information when you're doing development and debugging work. The board's got 2 CAN bus channels, which include local 120 ohm termination, and also a couple of D sub connectors for convenient connection, and they are pinned out in the fairly sort of industry standard pin out. So that will assist connection. We also have a couple of UARTs, 8 Thermistor interfaces. Now these have sort of been borrowed from our flight model, and they're intended to be used with 10 kilo ohm negative temperature coefficient thermistors. And all you have to do is connect those thermistors directly to the board to enable you to measure temperatures. We've got 31 general purpose I/O lines, and these can be configured however you wish as inputs or outputs. And the processor itself has various options for doing things like switching in internal pull resistors, and also the output drive characteristics when they're used as outputs. We've got a local 3.3 volt regulator because the board electronics actually runs from 3.3 volts, so it basically regulates down from the USB supply. Towards the left-hand end, we've got a few push buttons, one for resetting the microcontroller, a couple for general purpose test use, 3 status LEDs for test use, and those buttons and LEDs that I've mentioned you can use however you wish. We have actually got 2 additional power status LEDs, which just provide confidence that your power rails are switched on. And the chip also includes a real-time clock that you can use if you wish. Okay, so the form factor. It is slightly larger than the sister CubeSat board, basically because we made it a convenient size for use on the bench and for development activities. So it is actually a standard Eurocard size. The area in red that you can see on the diagram below, that is effectively where the core functions are that would fit within a PC104 profile as used in a CubeSat. So you can sort of see where we've sourced some of the design from. The other thing I'll quickly add is that, and it's not particularly apparent in this view, is that the main connector has been split into 2 areas, and you can just about see on the silk screen there that there are lots of labels in white showing what all the pins do, which is nice and convenient. So you don't actually have to constantly refer back to documentation to sort of find that a particular signal is on pin 27 and then have to count along the connector. So it makes it quite easy to connect to particular functions. Okay, thanks, Paul. This is a much better view actually of the board. This is actually a CAD generated view rather than a picture of the real thing, but it does actually demonstrate the ident labels that I mentioned just now. Okay. Right, so this is the only part of the schematic diagram that I am going to show you today. So this is like what we put on the first page of a schematic diagram, which is a block diagram of the remainder of the schematic, just to sort of give a top level view of the circuit configuration and how things connect together. So as you can see, the STM micro is towards the right hand end, and towards the to the right of it, you've got various bits of decoding and the static RAM, which was mentioned, and also the ST-Link. And then moving left, we've got the various interfaces going towards the main connector, which you can actually use as you wish and make connections. And then obviously onto the debug area. So that sort of block diagram loosely follows the layout of the board. Okay, thanks, Paul. Okay, now the STM microcontroller, I was going to cover a few of its functional features as opposed to what Paul went through earlier, which was sort of more from a higher level perspective. It does give you a broad range of onboard features, which are quite useful. So yes, we've got a 32-bit ARM M7 core. There's 2 megabytes of onboard flash, which you can use for your program storage, and 1 megabyte of internal RAM. It's got what they call a flexible memory controller, which is what STM have implemented as an interface to various types of memory that you can, external memory that you can use with this particular microcontroller. And that interface is actually used to talk to the SRAM that's on the board. So you do need to know about that. The device has also got internal power management, so you can actually sort of set various voltages and power consumptions inside the chip, depending on how hard you're using it and what features you want to use. It's got a watchdog. It's got multiple communication peripherals, including CAN, I2C, SPI, and UART, and quite a few of those peripherals do actually come out to those 31 GPIO lines if you wish to use any of them. It's got an ADC, some timers and a real-time clock, and I've already mentioned a large number of I/O ports. And finally, yes, the ST-Link, which kind of is a sort of an implementation of a JTAG as well. Okay. Okay, so you'll be needing some more information about this microcontroller. So there's 2 primary items that you'll probably want, and these are the sort of the details. The first one is just a basic data sheet that STM provide. It's about 350 odd pages, something like that, so it's quite substantial. And the other one is the reference manual, which is vastly longer and goes into minute detail about how to use all of the functions of the microcontroller. So well worth getting hold of that information. Okay, so now I'm sort of going to cover some of the electrical interfaces in a little bit more detail. Not a great deal to say about this one, the power source. This is designed so that you don't actually have to use some sort of bench power supply. If you've got your board, you can just plug it into a USB charger or indeed a PC and power it that way. And the power supply, sorry, the power consumption is not particularly high on this board, so it's well within the half amp USB limit. Okay, Dumple. Okay, clocks. The board itself has two crystals. The main one is 25 megahertz crystal, which is used by the main clock source. And then there's also a 32 kilohertz, which is used for the real-time clock function. Now, the MCU does actually have an extensive internal clock system to derive all sorts of frequencies required for various peripherals. So when you actually come to use the board, you can actually set up which peripherals get their clocks from which sources and how fast various parts of the system run. Okay, now the SRAM. I've mentioned the SRAM already. It's basically got two SRAM chips for general purpose use, and they are basically complementing the RAM that's inside the MCU. The next line sort of details what they are. They're made by an outfit called ISSI, and there's the part number, which again, you can choose to get the data sheet if you wish. This type of device, they're actually use an slightly more old-fashioned parallel bus, so where you actually have like an address and a data bus, and control lines to actually sort of control read and write cycles. So there are quite a lot of lines going from the MCU to the RAM, in that more traditional approach. So the FMC actually operates that interface, and that actually permits access as 8 or 16-bit modes. So you can either talk to it as bytes or words. It's entirely up to you. Our test software has an example of implementation. Indeed, the test software actually does exercise the SRAM to actually prove that it works, and you can actually read and write information to and from it. And just to help out, the board includes a bunch of test points on selected signals that are associated with the the SRAM. So if you do run into any problems, you can monitor those with a scope or a logic analyzer to sort of debug what's going on. Okay, the ST-Link interface has been mentioned, and this is the primary method by which we connect to it for programming and debugging. So it connects to the PC, to a PC via the USB link, and it includes a UART for general use, which I've mentioned before. So the type of ST-Link required is called is listed there. It's the version 3, and it's made by STM, typically available for about £40. So it's not too costly. And this picture actually shows the same module upside down with the lid off, just to sort of give you a look at what it's like. And as you can see, it connects to the board in question with a short ribbon cable, and that gives you all the functionality you need to download the firmware and access the debug functions. Okay, 2 CAN bus channels. Now, the CAN bus is advocated by KISPE for sort of future serial communications within small satellites because it has several advantages over their other alternatives. So obviously, it gives you robust differential signaling rather than ground reference signaling. So you get good data integrity and low EMI emissions. There's also good availability of buffer chips with automotive temperature ranges. It's a multi-drop bus. It's got error detection, good speed, and as I said before, on this particular board, you've got connection via those 2 D-sub connectors, but you can also actually connect via the PC104 connectors as well. And as an aside, I will also mention that on the OSSAT YouTube channel, there is actually a feature about the CAN bus, which will actually provide some more explanation as to what it's all about and why we think it's a good idea. Okay, so we've also got 2 UART interfaces. So these again are configurable from inside the MCU, and those are in addition to the UART interface that's on the ST-Link adapter, so you can use the UARTs for whatever you wish. 8 thermistor channels. It's almost a little bit of repetition here that you can connect 10k ohm thermistors for this. We've got a no-stall usable temperature range of -40 to over 100 degrees C. And then the board itself provides the necessary drive signaling and conditioning to operate those thermistors. So you don't actually have to add any more electronics or do anything else. You just connect the thermistor directly to the board, and then the temperatures are read via the ADC on the MCU. And then obviously there'll be some conversion to actually convert the ADC readings to real temperatures. And I'll just linger on that last one a bit. The manual that I'm going to mention shortly, that actually sort of gives you more details about how to actually access and convert to a temperature. Right, sorry, Paul, ready now. Okay, and then 31 general purpose I/O lines. So these are all accessible via the PC104 connectors. They're usable for general purpose inputs and outputs, or quite a lot of them actually go to the dedicated peripherals that are on the MCU. So those include things like timers, additional UARTs, SPI interfaces, and I2C. Now, at the bottom there, as I said, KISPE recommends that we use CAN buses for onboard ongoing projects. So while having said that, we do accept that some of you might be interested in using the SPI, and it's fairly easy to interface this board with an SPI system, just by connecting to the right lines and applying the requisite pull-up resistors. Okay, I've mentioned the debugging functions briefly before. So that picture actually shows what's effectively the debugging area of the board. And as I said, you've got like the button that's at top towards the sort of top left of that picture is an MCU reset button. We've got a couple of power status LEDs, 2 push buttons for general use and 3 status LEDs for general use. And that yellow wire is sort of just giving an example of connecting into the connectors there. So you're free to connect to any of those signals on those connectors. Okay, now a bit about building and testing the board. What we provide is a full set of files for the board. So that includes the design source files. So these are actually provided in Eagle CAD format for reasonable compatibility. It was actually drawn in Fusion 360, but we've chosen to go with Eagle format as a slightly older and probably more compatible source file format. So hopefully more people will be able to read those in directly. And those source files include the schematic design, the PCB, and also a library file. So hopefully you should be able to read those into your system and get the board design up on screen. And then obviously you can modify it or look at it as you wish. There's also the schematic as a PDF, PCB manufacturing files, including Gerbers, the bill of materials, and there's also actually a pick and place file there. So those are obviously what you need just to build a bare board and then stuff it with components. And then obviously also a test document. So that takes you through how to actually verify that your board is actually working after you've built it. So full details are provided in the manual, which is on GitHub. Okay, and this last slide here is, the last slide for me is just a list of the documents and files associated with building the board. So I'm looking at the time. The time's getting on, so I won't linger on going through each one of those in turn. But obviously they are there. They are also all on GitHub and listed on like the the README introduction on GitHub as well. So you can find that information there as well. I think that's all of my slides. Is it, Paul? Yes. So that's just the last one. That's the end of my talk, and those pictures are just of the board under test in the lab. So over to have you got some more to do, Paul, or is it Vicky?
Yeah. So just to sort of reflect on what the board can be used for. So if you become a collaborator, you can access our onboard computer application software. So that's the code that we're running on the spacecraft, and you can contribute to OSSAT by authoring onboard software, which would be fantastic for us, would be interesting for yourself. We've had a lot of people who engage with us to learn a little bit about space things, whether they come from the space domain or not. So there's a fair degree of fun that can be had there. You can also integrate it with SparkFun, Adafruit, I2C Slave hardware for general development fun. If we've done that. We've had it up and running with motor controllers and magnetometers and accelerometers and all sorts of things. All quite simple to integrate with the SparkFun and Adafruit type stuff. Other boards exist. So most notable one is probably the ST Nucleo H753, which is a development board that ST themselves sell. Now we started using that, and we were using that ourselves, but the problem that we encountered with that board is that there's no external memory to the processor, so it's tricky to get a file system running on that board, and that's kind of forced us into a situation where we have to develop our own development board alongside the flight model as well. But it is representative enough of our actual flight model to run the flight model code directly on this development board. So yeah, and you can modify the design. Unlike other development boards, you can take you can fork our repository, make changes to the design, and create your own hardware that meets your own specific needs. You can access all of this on our GitHub. This is the address right here. So it's open-source-satellite OSSAT_OBC_dev_board. And you'll find all the information that we've mentioned, the source schematics, the bill of materials, the test software that allows you to test the board, everything that you could need to basically produce, build, and test this onboard computer.
Lovely. Well, thank you very much, guys, for that. It's very much appreciated. So appreciate there was a lot of information to get through in quite a short time, but I think it was a really nice overview of how we've gotten to where we are, why we've picked what we've picked, and also what it is that our board can do. Now, we'd like to open the floor up to questions. I know we've got a couple in the chat already, and perhaps if anyone else has any, maybe you can use either the chat function or the raise hand, and we'll make sure we get round everybody. But I think the first one in the chat is around how close this board is to an Arduino, and if the contributors want to use one, how do they get access to it? Now, we actually have our boss, John Paffett, on the call. So I don't know, John, whether you want to just talk to this one a little bit.
Yeah, I can do, and I'm just going to put a response in the chat as well. So let's break it into two parts. So first of all, Arduino compatibility. So at the moment, the STM32H753 isn't supported natively through the Arduino IDE. There is a way of creating a variant and putting it on the IDE, so we're quite keen to explore that and get a version of the Arduino code working on it. But we haven't done that yet, so it's not natively supported. But if anybody out there is interested in doing that, then by all means let us know, because that'd be really good for some of the sort of basic and introductory type stuff that we're keen to support. In terms of getting your hands on one of the boards, so we are looking in the future to make them available. At the moment, I don't know if you're aware, but there's a bit of a chip shortage which has affected a lot of microcontrollers and other devices. As soon as we can replenish our stock, then basically we will be making those boards available. So just keep an eye out and watch your space, and we'll keep you posted.
Perfect, lovely. Thank you very much, John, for that answer. Hopefully that answers that question there. Paul, I'm going to throw this one your way, so I apologise in advance. Hopefully you're the most appropriate person for it. There's a question about why we looked at the STM32H rather than the STM32L series, so that's a low power for flight. I don't know whether that was one that you looked at when you were exploring the options.
Yeah, we did have a look at across the STM32 range, and given the criteria that we had, basically the most the one that matched our criteria the best with the sort of simplest architecture. It's a single core, it's not multi-core. Was this STM32H753.
Lovely, thank you, Paul. We had a request for the GitHub link, so hopefully I've popped that in the chat and hopefully people can access that. We'll also make that available on our LinkedIn and website as well. Okay, sorry, just wanted to come in. So what are the open items or the next steps for software bring up in this development board? I'd love to contribute. I think, Paul, that's probably another one to throw in your direction as a software related.
Yay, there's another one. So yeah, it'll be welcome to talk to you about, contributing to the software side of things. We're currently developing the sort of CCSDS communications between the ground and this board. So that's one of our current developments. We're developing the code that will allow us to talk to the ground with some known sort of communications protocols. We're also working on telemetry capture, how we get data off onboard data buses and store it onboard the onboard computer to be relayed to the ground. So that's another active thing that we're getting going with. And then there's some improvements that we've made. We need to make to some of the existing software as well, particularly around operational timetables, which I mentioned briefly earlier on. So we have this notion of an operational timetable, which is a list of instructions which are provided from the ground to the spacecraft in a file format. And the spacecraft opens up the file and goes through the list of instructions to allow it to schedule activities in space. And there's some improvements that we need to make in that area. So, in short, there's a fair amount of things that we could direct people in, and we've got people with varying levels of experience as well. So some people are fairly new to this kind of thing, and we're trying to marry people up with suitable developments that allow them to engage with things that are sort of that they can cope with, given the time that they can offer.
Awesome, lovely, Paul. And we will put up some links at the end, which show how you could, how you can register your interest. And so Paul or one of the team can drop you a line and have a chat. We have another question. Hopefully, Kevin or Paul, one of you field this one, about how much of the memory is non-volatile.
Yeah, I can answer that if that's right, Kev.
Yes, fine. Yeah.
Yeah. So this development board has on it the STM32, and that has flash memory within it that is used to store the program predominantly. So not really. I can see in your question there, Ed, you're thinking about a packet store. So that's not really suitable as a packet store particularly. But our flight model uses a memory called MRAM, which is it's been around for a little while, but it's non-volatile memory. So essentially all of the external memory that is used to hold all of the files and all the data is non-volatile. And the reason we've chosen MRAM is because it shows extremely good sort of properties with regard to radiation.
But I guess it's fair to say, Paul, on this dev board version where we use the SRAM, that's obviously not the case.
That's right. Yeah, you take the power away and the data's gone. Yeah.
Yeah. Okay, lovely. Well, I'm conscious of the time, and I'm sure some people will need to escape. So what I suggest is we, Paul, if it's okay, we move on to the next slide. If you do have more questions, do feel free to send them through. And as I say, at the end, we'll put up our contact details. So you can send us some more questions. We'd love to hear from you. We also do use our LinkedIn page. So you're also more than welcome to leave us some comments or send us some messages via that as well. But hopefully today, I mean, we're really excited, to have our first piece of, open source hardware out into the world. And as some of you may appreciate, open source software is quite a prevalent community, but open source hardware is still kind of, there's not as much of that as around as perhaps things like open source software. So we're really excited to be able to contribute to the open source community and to the open source space community and get that out there. So hopefully, you guys can see we're doing what we think is really exciting stuff, and hopefully you think the same. And we would love to get more people involved. As Paul has kind of alluded to, there's a lot of interesting software work going on, but that's not all. We have lots of other avenues as well, because there's lots of bits that go into making up a spacecraft. And so, if you would like to find out more or interested in contributing, then please do get in touch. We're running kind of some designathons. You could get involved in some of our kind of mini projects. You also may go, hey, I'd quite like to have a go at flying your open source satellite. Maybe you'd like to be one of the early adopters of our design. So, please do get in touch. Our next session is the 20th of April, and for those of you who haven't been to our sessions before, they tend to be quite varied. Sometimes we talk about topics like this, what we've been doing actually on the open source satellite, but other times we have kind of general interest space talks. So I think one of ours, we talked about kind of black holes and things, and other times, we talk about sort of general kind of open source community topics and things. So if you're kind of sitting here going, oh, I've got this thing and I think it'd be really good to share with a wider community, then please do let us know, because we're more than happy for our collaborators to come along and give a talk in one of these forums. We'd be really excited to. We had a really good one last year from Dawn Aero, who gave us like a crash course on all things propulsion. So we're really interested to have kind of different people come along and share some of their knowledge and experience of space with a view of really fostering this good open source space community. So yeah, so we've got our next topic, our next session on the 20th of April. We're going to confirm the topic nearer the time, but as I say, if you have anything you might like to contribute, then give it a shout. And with that in mind, Paul, if you just want to throw up the last slide for me. Here are all the ways that you can get involved. So we have a website. I think pretty sure if you just Google open source satellite, we're like pretty much the first hit that comes up. But we do have a website. There's a register link there, which you can use to kind of sign up and show your interest. As I've mentioned a couple of times already, we have a LinkedIn page, and that's a really good way to keep up with all the news. And that will have all of the links to our past videos. They're all put up via YouTube, and this one will be as well. We have a Twitter. We also have an email address, and at the bottom there is where we're located. So hopefully, by one of the many means, you'll be able to get hold of us and talk to us about anything and everything open source and space. So it just leaves me now to bring this session to a close. I want to thank Paul and Kevin for giving us that presentation, that walkthrough of our open source satellite development board. We need to give it a snazzy name, guys. That's the one thing we've missed. So maybe we should invite some suggestions. If you have some suggestions for a cool name for our board, throw it in. It's always more fun when things have cool names. But yeah,
could we call it Brian?
Possibly. But yeah, let's thank you so much for doing that, and say hopefully you can join our keep in touch, keep an eye on our accounts, and hopefully we'll have some more exciting news to share with you all soon. But yeah, and if you do go in and have a look on the GitHub and have a look at the design and other bits and pieces, please do feel free to leave comments on there and things. We'll pick those up, and we will be very interested to see what you have to think. Or have to think. I know it's the end of the long day now. But anyways, thank you very much, everybody, and we'll speak to you all soon, hopefully. So thank you very much.
Yep. Thank you, guys.
Thank you. Bye.